Okay, so this afternoon we will discuss about equivalence relations. Last meeting, we discussed different types of functions. Okay, can you recall different types of functions? Okay, there are three types of functions. The first is injective or injunctions. The second is surjective functions, and the third is bijective function or bijections. Okay, this afternoon we will focus our attention to equivalence relations. Okay, now let's begin by recalling the different types of relations. Okay, there are several types of relations, and you know that we have one-to-one, one-to-many, and many-to-one, and many-to-many. So there are four types of relations. So you can see here, yan, one-to-one, one element in X or in the domain is paired to one element in the range. If each first component and each second component only appears once in the relation, then it's one-to-one. One-to-many, yan, that's can be depicted by the arrow diagram. Yan, one-to-many and then many. Two is considered many. Okay, so many-to-one and many-to-many. But how do we define a relation? Mathematically, how do we define a relation? Okay, a relation could be defined as a subset of the Cartesian product. Okay, subset of the Cartesian product. Yan, is a subset of the Cartesian product. For example, let there be two sets. Set A, whose elements are 1, 2, 3, 4, 5. Set B, same elements. Okay, these are equal sets. Find A cross B. Or, since you notice that A and B are exactly the same, we can even have find A cross A. Okay, A cross A. Okay, what do we mean by this? Set of all possible ordered pairs such that the first elements come from A and the second elements come from B. Okay, so if we list down all the elements of A cross B, the elements would consist of yan, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 4, 1, 4, 2, 4, 4, 3, 4, 4, 4, 5, 5, 1, 5, 2, 5, 3, 5, 4, and 5, 5. So it's a set of ordered pairs. If we get any subset of that set, then we can have a relation. Okay? And we can define a relation by certain conditions. For example, okay, look at number 2. Find A cross B such that, or a set of all ordered pairs AB such that the first element A is less than B. Okay? So identify all those ordered pairs that satisfy the condition A is less than B. Can you see the board? Yes, ma'am. Okay, your set A consists of the elements 1, 2, 3, 4, 5. In fact, A and B are equal. So, we can even have it as A cross A. Okay, because B and A anyway are the same. B is also the set consisting of the elements 1, 2, 3, 4, and 5. Okay? So, A cross A will consist of the ordered pairs, or A cross B, to be consistent with what appears in your handout or on the slide. A cross B, pair all the elements of A to the elements of B. So we shall come up with a set of ordered pairs. Okay? the set of ordered pairs 1, 1, 1, 3, 1, 4, 1, 5, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, and 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 5, 1, 5, 2, 5, 3, 5, 4, and 5, 5. So all in all, how many elements are there for A cross B? There are 25. Okay? 5 times 5, 25. Now, let's look into the first, okay, or the second rather. The relation is set of all ordered pairs. So when we speak of relation, then put this in mind, we also refer to it as set of ordered pairs. Okay? So set of ordered pairs. Now going back, find number 2. This is supposed to be number 2. Find A cross B such that A is less than B. Okay, so referring to this, find all ordered pairs such that the first number is less than the second number. A is less than B. So what will this be? This set will consist of which elements? Is this included? This 1, 2? Okay, so this will include 1, 2 because 1 is less than 2, correct? 1, 3, 1, 4, 1, 5. Next, 2, 1. Is 2, 1 included? No. Okay, so 2, 3, 2, 4, 2, 5. Then from here, what's next? 3, 4, 3, 5. And then, okay, 4, 5. How about this? Okay, no more. Okay, so this set will consist of the ordered pairs 1, 2, 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, and 4, 5. Okay, and 4, 5. Okay, now, can you identify the elements of this set? How about A cross B, or set of all ordered pairs, AB, such that A divides B. Okay, can you list down? A divides B. Set of all ordered pairs such that A divides B. Okay, let me write that as, let's say, number 3. Number 3. Set of all ordered pairs such that, can you see this? Okay, that is read as such that A divides B. From your number theory, A divides B. A divides B. Okay, can you identify all the elements of this relation? A divides B. The first number divides the second number. Okay, what will the elements be? What will our ordered pairs be? Is 1, 1 included? 1, 1, 1, 2, 1, 3, 1, 4. Alright, let's list down. 1, 1. 1, 2. 1, 3. 1, 4. 1, 5. What else? 2, 2. Correct? How about 2, 3? No. 2, 4. Correct? Next. Anything else? Okay. 3, 3. Okay, next. 4, 4. And finally, 5, 5. Okay. So, these are the elements of this relation. All ordered pairs such that the first number divides the second number. In short, the first number is a factor of the second number. Are there questions here? Okay, is 1 a factor of 1? Yes. 1 a factor of 2, 1 a factor of 3, 1 a factor of 4, 2 a factor of 2, yes. 2 a factor of 4, yes. Okay, or the second number is divisible by the first number. Okay? The second number is divisible by the second number. So let's continue from where we ended from. Okay, so here is another example. Let A be, okay, the set 2, 4, 6, 8 and R is a relation on A defined by set of all ordered pairs xy, element of the relation such that x divides y. Okay, such that x divides y. How is this read? Let me read it. Let A be the set consisting of the elements 2, 4, 6, 8. And R here refers to the relation. Okay? The relation. Okay? How are the numbers being matched? What is the rule? Okay? That assigns one number to another number. R. That is R. Okay? Let A be the set 2, 4, 6, 8. And the relation R on A is defined by set of all ordered pairs xy, which are elements of the relation such that x divides y. Parang ganito. Okay? X, the first number, divides y. Okay? So, let's look into R. 2, 2, 2, 4, 2, 6, 2, 8, 4, 4, 4, 8, 6, 6, and 8, 8. Are there questions here? Okay, ito pa. The Simpsons family. Let S be Homer, Marge, Bart, Lisa, and Maggie. S cross S, a mapping of the set unto itself. Okay? S cross S. So if I would ask you, what is the geometric interpretation of R cross R? Sige nga, let me see if you can visualize. May I erase this part now? Okay, let R be your set of real numbers. What is R cross R? What is R cross R? R cross R. What's the geometric meaning or the geometric interpretation of R cross R? Can you visualize our real numbers? Okay, go back. What is our visual representation of the set of real numbers? Go back to your previous algebra classes. The set of points on the number line, isn't it? Is R. Oh, correct. Jeric said the number line. The number line, because it's infinite. Okay, the two arrows on both ends. Okay, the arrows on both ends signify that we could continue endlessly on both directions. 0 to positive infinity, 0 to negative infinity, that's R. So if I have R cross R, anong labas nun? R cross R. R cross R. Set of all ordered pairs, where in the first number, or should I say the domain is the set of real numbers, the range is the set of real numbers. What's the geometric meaning of that? It's the, isn't it the Cartesian plane? Ito, R cross R. Diba? Set of all ordered pairs such that X, Y are real numbers. It's the, kaya nga, Cartesian product. Okay? This is why R cross R is called Cartesian product, because if we plot all the elements of R cross R, it's in fact the Cartesian plane. It's the Cartesian product. So 0, 0, 0, negative 1, and so on and so forth. Okay? Cartesian product. Do not forget that. So your Cartesian product, the geometric interpretation, or should I say, represented by your Cartesian plane. Now, we move on to our goal for this afternoon, to define an equivalence relation. Okay, equivalence relation, what is it? What do we mean by an equivalence relation? Equivalence relation is a relation such that it satisfies three properties. The first property is reflexive property, reflexivity. A is an element of the relation. A quantity is related to itself. If AA is an element of R, then we say it is, or it satisfies the reflexive property. The relation is reflexive. How about symmetry or symmetric property? If AB, if the ordered pair AB is an element of R, and BA, okay, swapping their places, right? BA is an element of R, then the relation is symmetric, or it has the symmetric property. Or in other words, if A is related to B and B is related to A, then the relation is symmetric. How about transitive property or transitivity? Transitive, from the word transfer. If AB is an element of R and BC is an element of the relation, then AC is an element of R. If the relation satisfies this condition, then the relation is transitive. Or, if A is related to B and B is related to C, then A is related to C. That's your transitive property. Now, if a relation satisfies all the three properties, then R is an equivalence relation. Okay? So please take note of that. It has to satisfy the three properties. It should satisfy the three properties of reflexivity, symmetry, and transitivity. Reflexive property, symmetric property, and transitive property. Now let's look into some examples of equivalence relations. Look into the example of an equivalence relation. Yeah. Let A be a set and R is a relation on set A. R is an equivalence relation if and only if R is reflexive, symmetric, and transitive. Let's look into the example. Let A be the set whose elements are 1, 2, 3. Let A be the elements whose set are 1, or whose elements rather. Let A be the set whose elements are 1, 2, 3. And let R1, the first relation, be the set whose elements are 1, 1, and 3, 3. Okay. So, the relation from set A which is R1, consists of the elements 1, 1, 2, 2, and 3, 3. Question number 1. Is R1 reflexive? Is R1 reflexive? Yan, obviously. Okay? R1 is reflexive. 1 is related to itself. 1 is related to 1. 2 is related to 2. 3 is related to 3. Yes. Okay? Next is R2 or R1, referring to the same relation, symmetric? Is it symmetric? 1 is related to 1. If we change their places, 1 is related to 1. 2 is related to 2. 2 is related to 2. Still a member of the relation. 3 is related to 3. And to interchange their places, 3 is related to 3. And therefore, R1 is symmetric. Okay, so yes. Next is R1 transitive? Is R1 transitive? Okay, let's go back to the slide. Is R1 transitive? 1 is related to 1. 1 is related to 1. Okay? 1 is related to 1. 3 is related to 3. 3 related to 3. 3 related to 3. This is also transitive. Okay? The equal relation is an equivalence relation. So this is also transitive. Therefore, R1 is an equivalence relation. Okay, it may not be very clear to you yet, but if we proceed to the second example, you will find out, or you will have a clearer or a better understanding of equivalence relation. Now, let's proceed to example number 2. The equal relation is an equivalence relation. This relation, in fact, is equal. A equals B. A equals B, A equals B. The first and the second are equal. So, equivalence, equal. The equal to relation is an equivalence relation. Now, moving on to the second example, may I erase this now so we can have example number 1. Let the set be, the set given consists of the elements 0, 1, 2. And the following are the relations. R1 consists of the elements 0, 0, 1, 1, 0, 1, and 0, 1, and 1, 0. And then R2, 0, 0, 1, 1, 2, 2, 0, 1, 1, 2. Then R3, 0, 0, 1, 1, 2, 2, 0, 1, R3, RT, 0, 0, 1, 1, 2, 2, 0, 1, 1, 2, R4, 0, 0, 1, 1, 2, 2, 0, 1, 0, 2, 1, 0, 1, 2, 2, 0, and 2, 1. Okay, let's look into the three properties and decide whether the given or the relation identified is equivalence or not. Equivalence relation or not. Look at number 1. Did it satisfy? Oh, no. What is missing? What is missing? Okay, what ordered pair is missing? What ordered pair is missing? To satisfy reflexivity, the ordered pair 2, 2. Nandyan naman, di ba? Okay, the ordered pair 2, 2 is not part of the relation. Therefore, right away, we can say it is not an equivalence relation. You get it? How about letter B? Okay, let's look into, reflexivity. Did it satisfy reflexivity? So here, what is missing? Let me write in red ink. This does not contain 2, 2. So, it's not reflexive. How about here? What about the second relation? 0, 0, 1, 1, 2, 2. Did it satisfy the first property? Did it satisfy the first property of reflexivity? Yes. Now, proceed to the next property. Symmetry. Did it satisfy symmetry? 0, 0, 1, 1, 2, 2, 0, 1. Is 1, 0 a member of the set? Is 1, 0, looking at this, dito na lang 0, 1, if this is symmetric, then we should have 1, 0. Yes? Okay, wala siyang 1, 0. Therefore, what can we say about number 2? Equivalence relation or not? Not an equivalence relation. Okay? So, it's not an equivalence relation. How about R3? How about the third relation? Let's check on number 1 first, reflexivity. Did it satisfy reflexive property? A related to itself, element related to itself, meron. 0 related to 0, 1 related to 1, 2 related to 2. Okay, reflexive property satisfied. How about symmetry? Let's check. 0, 1, there should be 1, 0. Meron ba? Meron. 1, 2, meron bang 2, 1? Yes. Okay, but what is missing? 0, 2. Which one is missing? Okay. Okay, which one is missing? Okay, so first, some of you were responding. Wait, let me read your correct. We proceed to the next property. So it did satisfy reflexivity and symmetry. However, look at this. If 0 is related to 0 and 0 is related to 1, therefore 0 must be related to 1. Meron. 0 is related to 1. Look at this. To check on transitivity, 0 is related to 1. But 1 is related to 2. Therefore, by transitivity, there should be 0 related to 2. Okay? Dapat may ganon if it is transitive. But, look at the list. Do we have 0, 2? Is 0, 2 a member of R? A member of the relation? Wala. It's not. Therefore, this is not an equivalence relation. Okay, now we move on to the last. Okay, let's look into the last one. First, check on reflexivity. 0, 0, 1, 1, 2, 2. Okay, reflexive, check. Symmetry. Okay, 0, 1, 1, 0. There. 0, 2, 2, 0. There it is. 1, 0, 0, 1. 1, 2, 2, 1. Okay? 1, 2, 2, 1. So, symmetry is satisfied. So, reflexivity, symmetry, last. Transitivity. If 0 is related to 1, and 1 is related to 0, therefore 0 should be related to 0. Do we have 0, 0? Yes. If 1 is related to 1, and 1 is related to 0, therefore 1 should be related to 0. Do we have 1, 0? Yes. If 2 is related to 2, and 2 is related to 0, therefore 2, 0 should be a member of the relation. Yes. Next, if 2 is related to 0, and 0 is related to 2, therefore 2 must be related to 2. Meron ba? Yan, 2, 2. Okay, did we check on all the ordered pairs? Last, if 2 is related to 1, and 1 is related to, 1 is related to 2, therefore 2 is related to 2. 2 is part of the relation. Therefore, this is an example of an equivalence relation. Okay, because it satisfies all the three properties of reflexivity, transitivity, and symmetry. Do you have questions here? Now we proceed to the next. Moving on to the next. Now let the relation be, okay, for the second relation or the next example, next problem I should say. The next problem, let A, the set be 1, 2, 3, the set whose elements are 1, 2, 3, and R2 be the relation whose elements are 1, 1, 2, 2, 3, 3, and 3, 2. So, checking on the first property, 1 is related to 1, 1, 1 is a member of the set. 2 is related to 2, 2, 2 is a member of the set. 3 is related to 3, yes, 3 is a member of the set. So, first property, satisfied. Reflexivity is satisfied. How about symmetry? Okay, look. If we check on, 1, 1, 2, 2, 3, 3, symmetric right away na yan. But, looking at the last, 3, 2, 3, 2, then 2, 3 should be a member of the set. Is 2, 3 a member of the set? No. It's not found in R2. Therefore, it is not an equivalence relation. Got it? Next example. Okay, how about a relation defined such that x is less than y on the set 2, 3, 4? 2, 3, 4, what are the elements of R? R will be what? What are the elements of R? The elements of R are 2, 3, 2, 3, and 2, 4, 3, 4. Yes? Okay. 2, 3, or right away from the listing of the ordered pairs, right away, what can you say about the relation? Is it an equivalence relation? Looking at the first property, reflexivity. Did it satisfy reflexivity? No. Okay? It's not reflexive. Okay? Is it symmetric? No, not even. Okay? Not 2, 3, 3, 2. But, is it transitive? 2 is related to 3. And 3 is related to 4. Therefore, 2 is related to 4. Meron? Yes, transitive siya. Okay? Transitive siya, pero hindi siya symmetric at hindi siya reflexive. Next. Okay. May we answer number 1 together because I will leave numbers 3, 2, 3, 4 for you to do it on your own. Okay. May we answer number 1 together. Let R be the relation on the set such that R is equal to the set of ordered pairs xy where 3 such that 3 divides x plus y. Okay. 3 divides x plus y on the set. The set specified is 1, 2, 3, 4, 5. Okay, let R be defined on the set 1, 2, 3, 4, 5. Okay. Okay, first thing we have to do, list down the elements of R. Okay, let's list down the elements of R. What are the elements of R? Basing from the definition of the relation. Set of all ordered pairs xy. The relation is set of all ordered pairs xy such that 3 divides x plus y. Okay, from the set 1, 2, 3, 4, 5. Can you identify all the elements of R? 3 divides x plus y. What are they? 3 divides x plus y. Okay, 1, 2. What else? Okay, 1, 5. What else? Okay, 2, 4. Anything else? 4, 2. What else? 5, 1. Correct? Ano pa? 1, 2, 2, 1. Yes? 2, 1. Anything else? 1, 2, 2, 1. 3, 3. And, meron pa. 4, 5, 5, 4. Yes? Sige. 4, 5. 5, 4. Okay. Property number 1. 5, 1. May 5, 1 na. O, meron. May 5, 1, 1, 5. Property number 1. Did it satisfy reflexivity? Is it reflexive? Oh, no. Okay? So, right away, we can say it's not an equivalence relation. But if I would ask you to continue checking on the other properties, check on the other properties. How about symmetry? Is it symmetric? Is it symmetric? Is the relation symmetric? 1, 2, do we have 2, 1? Yes. 1, 5, do we have 5, 1? Yes. 4, 2, do we have 2, 4? Yes, symmetric siya. How about transitivity? Okay? Transitivity. Meron ba siya? Transitive siya? Is it transitive? Let's see. 1, 2. 1 is related to 2. But 2 is related to 4. Therefore, 1 should be related to 4. Is 1, 4 part of the set? Or a member of R? No. Okay. So, it only satisfied one property. And that's the property of symmetry. Reflexivity and transitivity are not satisfied. Therefore, this is not an equivalence relation. Okay? Okay, goodbye everyone. This is all for this afternoon. We shall have another session next week. And that's the end of your chapter 1.